It's something we use every single second of the day. But be honest, do you know how it actually gets to you? Well, in this explainer, we're going to follow the amazing, invisible journey of electricity, all the way from the power plant right to the plug in your wall. Let's dive in. I mean, it really does feel like magic, right? You flip a switch, and bam, there's light. Instantly. But behind that one simple action is one of the most incredible engineering marvels of the modern world. So, how does that power travel hundreds, even thousands of miles in the blink of an eye? That is the exact question we're going to answer today. All right, let's start at the very beginning, the generating station. This is the starting line. It's where we take other forms of energy, like the intense heat from burning coal or the massive force of water rushing through a dam, and we transform it into the electricity that runs our entire world. Now, these power plants, they generate electricity at some very specific and very high voltages. We're talking about incredible levels of electrical pressure here, measured in what we call kilovolts or kV. And these numbers you see, from 11,000 all the way up to 33,000 volts, they aren't random. They're chosen for a really important reason. So that begs the question, right? Why not just crank it up to 1,000,000 volts and call it a day? Well, it's not that simple. The engineers who design these massive generators are performing this incredible, delicate balancing act. It all comes down to a really fundamental trade-off. And this right here perfectly explains that dilemma. See, on one side, you have electrical current. To handle a higher current, you need thicker, heavier, more expensive copper conductors to carry it. But on the other side, you have the voltage. And to handle higher voltage, you need thicker, more robust insulation to keep all that immense power safely contained. It's a constant push and pull between these two forces. So, what's the real roadblock? What's stopping us from generating power at even crazier high voltages? Well, the answer is surprisingly simple: logistics. These machines, the generators, they would become so unbelievably massive and heavy that we literally couldn't move them. We couldn't get them from the factory to the power plant on a truck or a train. It's a classic case of brilliant engineering bumping up against the limits of the real world. Okay, so we've successfully generated the power. Now we have to get it to where it's needed. This is where the transmission system comes in. And the best way to think about it is as a super highway for electricity. And just like any good highway, you need on-ramps and off-ramps, right? For our electrical superhighway, that job belongs to the transformer. It steps up the voltage to merge onto the highway for that long-distance trip, and then it steps down the voltage when it's time to take an exit to a local neighborhood. The whole process is actually pretty straightforward. First, right at the power plant, the voltage gets stepped way up. Then, that bulk power is transmitted super efficiently over long distances at that crazy high voltage. Finally, as it gets close to our homes and businesses, the voltage is stepped back down to a safer, more usable level. But wait a minute. If you have to lower the voltage at the end anyway, why even bother with all the hassle of raising it so high in the first place? It's a great question. And the answer is the secret sauce that makes our entire electrical grid so incredibly efficient. And here's the brilliant part. By cranking up the voltage, you can massively decrease the current you need to deliver the same amount of power. Think of it like a garden hose. If you increase the water pressure, a much smaller stream of water can do the same job. With electricity, A lower current means way less energy is wasted and lost as heat in the power lines. It's this simple principle that saves an absolutely enormous amount of energy. And the difference in voltage is just staggering. I mean, look at this. The big long-distance transmission lines can be humming along at 765,000 volts. Now compare that to the local distribution lines in your neighborhood, which are probably running at around 11,000 volts. That huge difference is exactly what makes efficient, long-distance power transmission possible. So we've seen how electricity is made and how it travels. But the system is so much more than just a wire from point A to point B. It's a massive interconnected network we call the grid. And to keep this whole thing running smoothly and safely, there's a team of invisible guardians working 24/7. So, what is the grid, really? Well, think of it less like a single highway and more like a huge, sprawling web of interconnected roads. This web links all the power plants to all of us, the consumers. It allows power to be instantly rerouted to meet demand anywhere in the system. If there's a problem on one path, the electricity just finds another way. It's all about reliability. Our first guardian is the senses of the grid, the measuring equipment. These are the eyes and ears of the whole operation, constantly monitoring the grid's vital signs, things like voltage, current, and frequency, giving operators a real-time picture of what's happening everywhere at every moment. Next up, we have the grid's immune system, the protecting equipment. So when something goes wrong, say a tree falls on a power line, devices called relays instantly detect that fault. They then signal a massive circuit breaker to trip, isolating the problem in just milliseconds. This is what stops a small local issue from cascading into a huge blackout. Then you have the traffic cops, the controlling equipment. Their job is to direct the flow of electricity across that huge web, making sure power gets where it's needed most. And just as important, they keep the frequency of the system perfectly stable. That precise, unwavering stability is what allows all of our sensitive electronics, from our clocks to our computers, to work properly. And our final guardian, the compensating equipment, which act as the balancers. They manage something called reactive power. Now, the best analogy is the foam on a beer. It doesn't quench your thirst, but you need it to keep the pressure and quality right. These balancers manage that foam, keeping the voltage stable and the entire grid running at peak efficiency. You know, building a grid like this is a monumental task. It can take decades. Just look at India. For over 22 years, they painstakingly connected their separate regional grids, one by one. And then, finally, on the very last day of 2013, the last piece connected, forming a single, unified national grid. It's just an incredible story of engineering and coordination on a national scale. So we've followed this incredible journey from the power plant across the country past all its guardians. But what is the ultimate goal? What's the whole point of this massive, complex system? Well, the goal is actually pretty simple, but it is incredibly important: to supply uninterrupted, high-quality power to everyone. That means keeping the lights on in our homes, running the machines in our hospitals, and powering our businesses 24/7. And the two key words there are uninterrupted and quality. So what does quality power actually mean? Well, this table breaks it down perfectly. You see, in an ideal world, the voltage and frequency would be perfectly, absolutely constant. But in reality, there are always going to be small fluctuations. The grid operators work tirelessly to keep these tiny variations within very strict allowable limits, because even a small deviation can mess with the performance and shorten the lifespan of all our electronics. So, from a spinning turbine to the very screen you're watching this on, the journey of electricity is truly remarkable. The grid is, without a doubt, one of the largest and most complex machines humanity has ever built. But, our world is changing, with renewable energy and electric cars becoming more common. This incredible machine has to evolve too, which leaves us with a pretty big question to think about. What will the next chapter in this amazing story look like?